Okay, so good morning. And so, what we see now, or rather, what I will see today, something a little different from cross coupling, but yet the name is cross coupling. And if you see the name, and the name implies it's an oxidation reaction. So, it's a dehydrogenation, all of us know it's an oxidation. So, dehydrogenative and in bracket I call oxidative and cross coupling. So, by now all of you have known what is the meaning of cross coupling, right? Cross coupling, what is the meaning? Grossly,
Stitching of two carbon bonds with a metal center, medium by metal center.
No, even it is broader. It could be carbon nitrogen also. Book wall cross coupling involves carbon nitrogen. Okay. So, and typically most of metals are of course palladium, and some cases nickel, some cases rhodium, and some cases many other metals also, but mostly. And so, that means the first if you summarize traditional I say cross coupling. So, and it could be abbreviated as traditional cross coupling. It should be abbreviated as what? What you need? It is a group it's in a heterocyclic chemistry. So, I will say het AR means heteroaryl, and then what? Then a metal or metalloid, right? And then you take one more, maybe heteroaryl maybe, and then X. So, and the product is so het aryl and het aryl combination product. So, it's a biaryl product. So, that is the traditional one. So, you have to recall that these sort of cross couplings would require a metalloid or metalloid or organometallics, you can say, or organometalloids, and then the corresponding the halogenated compounds, triplets and ammonium salt, all these diazonium salt, all these things. Okay. Then we have also seen something like called direct cross coupling. Direct cross coupling is something like you have a heteroatom, for a heteroaryl group and hydrogen. We have seen only one example, hetero again aryl and X. We have seen only one case in the last example. If you have a aryl CH with intermolecularly, this can go to the product. The product is again this is diaryl and biaryl. In this case, what you that means hydrogen is somewhat analogous to a metal, like silicon. Silicon we call some super hydrogen, means it is metal, but metalloid you can say. And so, that means it has some analogy with the hydrogen reactivity. And so, that means the direct cross coupling where we don't have a metal in it or metal derivatives. And then today's one dehydrogenative cross coupling. So, and what it is? It is now we can say hydrogen and one more heteroaryl, and there is no X, just basically hydrogen dimerization. So, dimerization, right? And what else? What are the other possibilities? There is a possibility, all of us know, but that sort of combinations are not very useful. What is the other possibility? In honors level, we have learned that if you have a carbon metal and a carbon metal, you can oxidatively dimerize, like sodium salt of ethyl acetoacetate treated with iodine, it gives the corresponding dimeric product. So, you can say two metalloids, that means heteroaryl metal and another heteroaryl metal can be oxidatively coupled to the corresponding biaryl compounds. And there is one more very interesting and quite very useful rather very useful coupling is coming up that is not well studied, but there is a possibility that in future this reaction could be a popular reaction. Again decarboxylative cross coupling. What it meant by that? It is an heteroaryl. Instead of the hydrogen, you can take a carboxylic acid, and then other reacting partner should be heteroaryl, like any other reactions like halogenations and etc. Okay. So, any other, that means in other words, by giving this chart I am trying to say that these sort of cross couplings are very broad. I mean almost any kind of combinations can be used to make a carbon-carbon bond formation between the two aryl unit or alkyl unit or heteroaryl units. Okay. Since our class is on heterocyclic chemistry, we will have example from heterocyclic, and today especially we will concentrate on basically the dehydrogenative. Dehydrogenative means at some point somewhere you need an oxidizing agent or an oxidant, and the catalyst obviously the metal and normally the palladium, it should be in a lesser quantity, means less than maybe 20 mole percent. Okay. One of the very first examples in this area was published in 1967. Historically this was again by a Japanese person called Moritani. What was the reaction? The reaction was a simple benzene and styrene. Okay. And of course, palladium acetate. So, from now onward I will write palladium acetate maybe PA. How is that? Abbreviate, because the palladium acetate in this lecture will come many times. So, I will write PA. So, okay. And an oxidizing agent. So, oxidizing agent is an oxidant. Oxidant many times is BQ. BQ is benzoquinone. And what do you get? Actually they were getting a product which is called stilbene, right? And previously how we made this compound starting with the corresponding bromo compound and this styrene, and then again this is the typical Heck reaction. But then you can go on writing things like this. Suppose if you have R here substituents, so you will have R here, obviously then you can have a broader utilities of these reactions. But these Moritani reaction, the first one, that means without any halogen, without any metal, you can do the cross coupling type of reactions, but the yield was poor, regioselectivity was poor, means if you have an R here you can get all kinds of products. Now, and thirdly they had to use a lot of excess amount of the arenes. I mean so that is basically wastage. Like in Friedel-Crafts reactions, you get you put lot of arenes, actually equivalent of arenes is more than the corresponding the acyl halides or aryl halides or alkyl halides. Okay. So, but it was an indication that it is possible that without a metal, and that sort of reactions has been tested in a non heterocyclic compound. Suppose you take acetanilide and then as usual an acrylate, in this case butyl, because it is little higher boiling, and again PA, I will say palladium acetate, percentage is very little, mole percent, and then BQ. So, mind it, now it is an oxidizing agent. So, 2 hydrogens are getting eliminated from this, that means what should be the equivalent? It should be at least 1 equivalent, because you have to remove 1 equivalent of this hydrogen, and the other catalyst is other toxic acid and acetic acid. Okay. So, throughout this, basically we will study the reactions, we will see the electronegativities, we will see the acidity, we will have a set of reaction conditions, and the products all of us know by now know. Products would be some sort of a biaryl, all these kind of things, and one of the components could be heterocycles. That is it. But while I write, you have to just note or rather take care of the types of the reagents we use, types of the oxidizing agents you use. We do not have many options though. There are very few options, very few. Okay, that is what you have to note, and also you have to note these homocoupling, etc. Why the homocoupling is not taking place, and particularly one, then regioselectivity, all these things. In this case, what do you expect? It's a, I mean, normally we do not expect any reaction, right? Because it is not satisfying the prerequisites of Heck reaction, Suzuki reactions, Negishi reactions, etc., etc. But it is again a new kind of reaction. So, if you see the product, you will find it is a nice way of. So, it is I should say it is known as alkynylation. That means a benzene ring is being alkynated, and the other portion is as it is this. This is a single product, and the percentage yield is 75%, 72%. So, what do you see here? That is what you have to see. You have to see the striking features of this reaction. Striking features. What do you see the striking feature? Is very orthoselective. Whenever you do reactions of electrophilic reactions like anilines, etc., all these things, they will definitely give you the para more, a larger quantity. But in this case, you have very orthoselective. Okay. And then what else? You do not require a metalloid like boron, Suzuki, and then zinc, magnesium, lithium. You do not need anything, just, and that too the palladium, you see, although it is very expensive, you require only 2 mole percent. Only disadvantage you can say benzoquinone. Benzoquinone is quite expensive, also in large scale it is not a welcome reagent, right. So, you will see some more reactions where you will the oxidant oxygen is the terminal oxidant. So, in that case those reactions are very good, they should be classified as the green reactions. Okay, any case that was an indication, and now if that is so, because if we recall aniline has some resemblance with an heterocycle. What is the heterocycle which resembles? Very good, pyrrole or pyrrole. Okay. So, that means if this works here, then the next reaction that should work, it should be pyrrole, and or and in this case it is the Bock, let us say. The nitrogen has to be protected, otherwise all of us know the pyrroles are susceptible to undergo oxidation, gives you what? Right. What is the polymer? Polypyrrole. No, in fact, there is a popular polymer called pani. What is it? Right, polyaniline. Discovered by few years ago by one American and one Japanese, Alan McDermott. Okay, he died a few years ago, and after receiving the Nobel Prize. So, that means what I mean to say, the heterocycles like anilines, they are susceptible to undergo oxidation. Furan, also these undergo acid catalyzed. So, you have to think about that, and so you need a protection here of the nitrogen, and we will see some of these cases. Probably we will see we do not have to do the protection though, if it is intermolecular reaction. So, in this case, let us say just we do not worry about the alkyl part, I write let us say R here or butyl whatever, and this again Pa means palladium percentage in this example it is 10 mole percent, and DMSO as the solvent, DMSO is the solvent with a mixture of, and in combination with dioxin. So, what is the expected product? See here, you see you do not require any metalloid, and the reaction is so good, you get this product. What is the oxidant? Oxygen. 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 So, that means you will find some of many examples here. And tricky thing about, I think we have already seen such a thing, and now means same reagent. Oh, sorry, okay. So, what do you expect? Same condition, only thing we have put a silicon here, triisopropyl silane, 3 positions. Actually, yes, and the yield is not mentioned, but it is supposed to be very good yield and tips and this. So, what boils down to is that it is not required to study Suzuki, Heck and all these things. That means, you can do without metals. Okay. There are many other examples. For example, let us say in case of now, I mean, you can just pick up any example. For example, in this it is a indole derivative, and it is benzoate, and do this again the same kind of reaction, reactions with acrylate, and obviously the product would be, I do not have to write, just you can abbreviate, again the product would be these Heck reactions. What is the advantage? Okay. So, I mean, you can do that means it is quite easy. What is the advantage? Advantage is that, so although you are doing a homologation by 1, 2, 3 carbon atoms, you can actually you do all kinds of manipulation, do the hydrolysis, convert into carboxylic acid, okay, do the decarboxylation, you get 2 carbon homologations. You do the ozonolysis, you get 1 carbon homologations. That means, once you have a 3 carbon functionalized 3 carbons, you can have all kinds of possible homologations. Okay. And next reaction would be again from an indole series, and now you see this little interesting. This is a tryptophan derivative, and then it is a prenylated compound, and it was very recently discovered, very recently discovered. And mind it, the temperature is pretty low, just room temperature. So, what do you expect? Cyclization. So, cyclization taking place. So, cyclization taking place, and but in this case, I mean, the cyclization is little again a tricky cyclization with a little bit of the rearrangements, and so what you get here, you get 1, 2, 3, 4, 5, 6, 7, 8. So, you get an 8-membered ring system, and nitrogen up here, ester up here, and then NaC and double bond, and which is little unusual though, this one, and you can sit down and work out the reaction mechanism. So, what could be the mechanism? Palladium acetate is an electrophile. So, if you have palladium acetate, that means if you have this thing, it will go to the palladium. So, you will have a carbocation here at the second position, and that becomes C2. Then you have a nucleophile here, that means you come to this and this nucleophile, then you get a carbocation here. The palladium then after oxidative, if you have palladium something, so it will again reductive elimination, you will go on this thing. Okay. And eventually what next? You see here, if let us say 1, 2, 3, 4, 5, 6, 7. So, you have to make it 8. You have to make it 8, that means it is a carbocation here, which is less likely though, it will undergo migration here. So, you get a positive charge, you get a positive charge. So, nitrogen this, and so nitrogen here, and sorry, okay, forget about it. Hydrogen, then this thing, and then let us say as nitrogen here, and now this should be plus, right, and then you have something like this, and obviously what next? I mean, all of us know is basically the eliminations. So, elimination to get to this compound.
I think palladium coordinates with a double bond and abstract the hydrogen, forming a hapto 4 type system, and the electron density on the tertiary carbon is more, so that's why that attacks. Allylic anion type coordinated with palladium hapto 4. Then that attacks with the pyrrole ring.
Then attacks with the pyrrole ring. That means carbon is directly attacking this. Okay, actually there are many examples. The indole chemistry has been so well established. So, apparently indole should be more nucleophilic in nature, okay, not the reverse.
Sir, how that two carbon is nucleophilic?
Which 2 carbon?
Sir, because the addition happens 2 carbon and the external
Right.
Carbon 3.
Yes.
How the
2 carbon, yes, in indole, if let us say 3 carbon is blocked, all the substitution reaction takes place at 3 positions. That is well established, that is well established, and so many examples. That is why this mechanism has been suggested this way. Okay. I mean, yes, you can argue all kinds of things. Let us look at like this one. One more example from the indole series. In this case, again palladium acetate. So, and what do we expect here? Palladium acetate. So, 3 position is blocked. 3 position, I mean, one can do, I mean, all kinds of things. I mean, you can do this activation here, and then reactions from this side and this thing eventually. So, that means one can expect a reaction and right, sorry, it should be 5 membered, then again it should 1, 2, 3, 4, 5. So, it is a 5, and one can expect a palladium up here, right, and this methyl, and what is that? Oh, yeah, why they have okay. Okay, fine. Now what? So now elimination. That's it. That means okay. That means you are losing palladium 0, and the product is what you get is. So, what it is eventually, if you look at eventually, and then palladium 0 must be converted into again palladium 2, and this sort of palladium 2 0 can be converted by simple oxygen, just one atmospheric, then one atmospheric oxygen is enough, oxygen 1 atmosphere is enough. And this, if you just look at the oxidation state of the starting material and the product, you will see it is nothing but it is an oxidation, and also if you compare the molecular formula, they differ only by 2 hydrogens. So, that is why these sort of reactions are known as oxidative coupling. And quite interestingly, if you do such things, I mean, like if you try to extend these sort of reactions to pyridine, this reaction would not take place. So, what is the requirement? So, that means most of the pi XSS molecule would be reacting, indole, pyrrole, thiophene, benzothiophene, all these things. So, these sort of oxidation reactions or decarboxylation dimerization reactions are less important in pyridine chemistry, but then someone has tried, and since we all know that this pyridine enoxide apparently it should be পেজগুলো উল্টে দেবো, ওকে, আচ্ছা আচ্ছা। So, pyridine enoxide, all of us know it is more electrophilic or nucleophilic, although we put an oxygen up here and nitrogen here, and in terms of nucleophilicity or electricity around the nuclear position, means the ring carbons, it is more nucleophilic, and if it is reacted with these acrylates, now it is a butyl acrylate, and once again the condition here is palladium acetate, and the mole percent is 10 mole percent, and what you are likely to get, and this, and I will not be able to explain to you why the regiochemistry is C2, but it gives you the C2 alkynylated product. So, it is a kind of a special case, probably it's increased electron density in the ring, all of due to the electron delocalization of the oxygen minus, all of us know, and this. Then what else you require? You require an oxidizing agent. In this case, this oxidizing agent is silver carbonate, and 1.5 equivalent, and then 100 degree centigrade. So long we have come across how many oxidant? First was benzoquinone, second was oxygen, third one is silver carbonate. Okay, and only recently again, I mean they are all different, only recently, very recently this sort of reactions has been extended to other heterocycles, but in this case of course it is a purine nucleus, and all nitrogens are protected, here. So, all of us know this purine has a skeleton of this kind, and if you have only one hydrogen functionalizable. So, imidazoles typically are nucleophilic in nature, and then the other again acrylates, butyl acrylates, and PA I write, then what else? This now the new oxidant here is a cupric acid, and the solvent is little different, DMA, dimethyl, NN dimethyl acetamide, little higher boiling, so you can temperature can be raised to 120, and then just so we can, all of us can now write the product, right, without any so product. So, once you have, that means in this case now oxidant is cupric acid, that is all. I mean and those sort of oxidations are chosen by doing lot of trial and error experiment, optimization experiments, most cases. And so I mean this paper has given so many examples. So many examples. So that means this sort of dehydrogenations with 5-member ring system is pretty general, useful. And now what I will show you something quite interesting. By different reaction conditions, you can direct the alkylations in different positions. This has been again published quite some time ago, and what you will find that with cupric acetate, the reaction goes to the 3 position in case of the indole. So, if you take indole here and without any protection of nitrogen, you see, that means these things are slowly changing, improving, that means no requirement of nitrogen protection. And same old thing, this acrylate and the reaction conditions. Reaction conditions are like this, again PA, palladium acetate, percentage is not given, and then cupric acetate. Solvent is DMF and DMSO combination, and the product is so that is an advantage here, that you do not require the protection of this thing, and the reaction takes place at C3. Thus I think all of us can write the mechanism, right? What is the mechanism? Just like see, what should be first step? First step should be that palladium, palladium goes here. So, and then aromatization takes place. So, just as if the indole is undergoing electrophilic substitution reactions with palladium. So, what you will find, this the reaction mechanism would involve something like this. That means, it is an organopalladium complex would be formed, and then once this is formed, what is equivalent to essentially the sort of this Heck reactions. So, eventually go to this one. Now, what is more striking, if you change the reaction conditions, this is a very general reactions. Actually, there are so many examples, I will not just burden you with many examples here. Now, just see the contrasting reaction conditions. Again, the same combination of the reagents, and the reaction condition involves again palladium acetate. Only 10%, 10 mole percent, sorry, it is something like 0.2. Okay, the thing is about like 0.2 equivalent is better. We will find out the percentage, and the oxidant here is different. Tertiary butyl BZ means benzoate. That means benzoate ester of tertiary butyl hydroperoxide, tertiary butyl. So, that is it. I mean, palladium acetate is common, only we are changing the oxidizing agents from time to time, and the solvent is dioxane, acetic acid. These are all typical polar solvent. So, dioxane, acetic acid, and temperature is not very high, it is 70 degree centigrade. So, what do you expect? Okay, expectation is, I mean, just by changing and this okay, I think in this case nitrogen is protected though, right. In this case and they do not say anything R1. Oh no, without protection yield is little poor. That means this nitrogen is without nitrogen protection yield is poor, around 50%, but if you protect this nitrogen, oh, that is kind of strange, okay. Nitrogen is not protected, okay, and the reaction gives you this. So, what is the explanation? What is the explanation? Okay. No, there is no radical actually. There is no radical actually. Okay, I will give you a hint. Let us say if you can come up with any particularly any kind of rather explanation. Here, if you have a methyl up here, there is no reaction. No reaction. Enoxide. Why enoxide would form? And pyrrole is not known to form enoxides. Indole. No reaction. Okay, let us look at if you have a palladium. So, all of us know that this would form a palladium kind of this acetate or something like this, right? And you have a hydrogen up here, okay. And by tuning the oxidation or oxidant, you can actually delay the oxidation. And then in that case, there are two ways. In the first case, the hydrogen was eliminated, rearomatization. So, depending on the nature of the oxidant, the cupric acetate was the oxidizing. So, if you have the cupric oxidate, then the oxidation probably, the aromatization probably, oxidative aromatization probably was faster. If you delay this, delay the oxidation, and this starts, then there is a likelihood that the palladium would migrate to this. Okay. So, that means hydrogen here, and you see, and that is also require the iminium kind of a salt here. And so, what do you see here? Then palladium and X and this hydrogen, and so you will have this. And what next? And this would then after palladium migration, then it aromatizes, and that could be then the typical Heck kind of reaction, reactions. So, that means you have to have a right oxidizing agent to promote this palladium migrations. You can delay the oxidation, and then once this palladium is excluded as palladium 0, then you do the slow oxidation to this. Okay. I think that could be on, and the reactions also takes longer time, like 18 hours. The previous one I have that also 18 hours. Okay. So, but it does not tell you anything though. And so, that means that you can at your will, you can just direct the positions of the substitutions or the alkylations in these dehydrogenative reactions. Okay. And then there are other kinds. So far we have talked about these, and then there are other reactions. Let us say there is a possibility also called alkynation, alkynylation. Okay. And what it is, that means in the place of acrylate, also you can use the corresponding alkyne, and you can get to this product. So, you can get to this product. What does it tell you? So, it is a substitute of Sono-Garcia reactions. You do not have to have an halogen, you do not have to have this. That means, if you have and the conditions here, but you have to look for the right kind of the combinations of the reagent. In this case, it is potassium tetrachloropalladate, potassium tetrachloropalladate. Okay. These combinations, of course, it comes with a little bit of experience. Then other base here is cesium carbonate, and very interestingly, this acid, an acid is required to protonate the nitrogen. So, pivaloic acid is 5 carbon, right, 5 carbon tertiary butyl carboxylic acid, right, okay, pivaloic acid, and of course, a solvent is required. And now, do we need any oxidizing agent? Do we need any oxidizing agent? Do you need any oxidizing agent? That is it. I mean, basically you have to compare the starting material and the product. If you see, just you do not have to even count for the, you count these oxidation levels of the starting materials and the products. In this case, it is so simple. The title says dehydrogenative reactions. So, you have 2 hydrogens are getting eliminated. That means, you need an oxidizing agent, and oxidizing agent is just oxygen, plain oxygen. Okay. And the catalyst is 10 more percent. So, I mean, once again, that means we have to little concentrate on the reaction conditions and see the outcome of the reaction, but mind it, then you do not have to use any kind of metals or metalloids. Okay. But there are say these sort of reactions can be extended to oxazole or thiazole, but then there is a little difference here. Take this again, alkyne, and here first they use, see this is I mean, it is quite, I mean, there are so many people are working on this. Basically, the fine tuning of these reactions conditions have to be done, and the palladium 0 is used. So, this is basically tetrakis triphenyl phosphine palladium complex, okay, as palladium, which is basically palladium 0, and toluene is the solvent. Then the product, because we are coming to the product of this dehydrogenative product. So, that means what you require is an oxidizing agent, and in this case again not even oxygen, it is just air is sufficient, okay. But what we knew that this sort of compounds undergoes lithiation. So, if you then if you use a base lithium tertiary butoxide, so the reactions proceeds in this smooth fashion, okay. That was, see, you have to just compare. The pyrrole can be protonated with pivaloic acid, and you can activate this C2 hydrogen, and then subsequently the reaction takes place. In this case, what you are doing, you are actually promoting the lithiations at these 2 position, and then eventually this oxidation and the pallidation, all these Suzuki Heck reactions or Sono-Garcia reactions are taking place, okay. So, at some point, that means you do not have to do a separate preparation of the organometallics, just in situ you can do it, and then do the subsequent reactions in presence of oxygen. And similar reactions. So, if you recall at the beginning of the class, what I asked, that what are the coupling reactions, and Anindya said is a CC bond formation reactions, but this is an example where you do not have is in carbon nitrogen bond formation. For example, if you take oxazole, benzoxazole and nitrogen secondary amine, and of course, that means there are two hydrogens. So, that means in a heterocycle can be aminated, that means functionalized with a nitrogen, that is it. That means if you did not know, so how do you do, let us say, how do you do? If you are given like an oxazole and try to incorporate in a dialkyl amino group at 2 positions, how would you do? If you did not know this answer, how would you have done? Okay. Lithiation followed by chloramine. Chloramine is not chloramine is very rarely used as aminating agent. So, in one of the earlier classes I said that amino triazole, that can be used in the as aminating agent and other vicarious substitution reactions. No, mechanistically what you said is mechanistically possible. You do the lithiation and then do this amination. Okay, fine, NH2 you get, then how do you do this selective alkylations R1 R2? That is tough. That is what you studied in BSc, right? Hinsberg, something like that. Not Hinsberg, Gabriel amination, right? So, you first protect that and then do side by side, because direct alkylation is a serious problem. Direct alkylation is a serious problem. So, that is why this reaction is quite very useful. I mean, most of the reactions actually have been published in very good journals. I mean, okay. I mean, so far whatever I have either from Chemcom or Orglade or Angumantesemi. That means these are very important topic. You can just directly functionalize, and the catalysts normally you have seen this oxygen. In this case also is cupric acetate, I mean sodium carbonate, then other combination is pyridine, toluene, all kinds of things. Okay. So, toluene and of course, oxygen is there, mind it. So, in sometimes you will see in the reaction condition they use pyridine, that means pyridine is not getting affected in this dehydrogenation process. Okay. So far we have done this alkynylation and I mean okay, previously alkynylation, and now let us look at whether this alkene can be substituted by an arene, just straightaway arene. And okay, I have one more example of amination. I think I will maybe we will see that. It is very common. Okay, let us say, I think I should take this example also. Take the example. This is again a reactions of a benz oxazole, and then other reactant is a coumarin, is a functionalized coumarin. You see here you have a methoxy, the other portion has a piperidine ring system with nitrogen. Fine. So, now you have to basically join these two positions selectively. How do you do? Say if you think of the lithiation etc., that means this nitrogen should be connected to this star carbon. Given these two substance, it will be tough. For example, lithiation etc. would not work. If you do a lithiation here, okay, and try to react with this, preferentially the lithium would undergo reactions with the lactone ring system. Think about anything, let us say if you say lithiation and then followed by transmetallation like organocuprate for example, there is a likelihood that the reaction would undergo conjugate addition organocuprides are well known for conjugate additions. So, undergo conjugate additions. Okay. Anything else you can think of? Any other metals? Let us say I mean you can do okay, lithiation followed by borylation. You can do all kinds of things, but in general that lithiation is tougher than the lithiation in simple aromatic chemistry. Okay. So, lithiation in heterocyclic chemistry is tougher than those in this aromatic chemistry. So, that means lithiation, magnesiation, all these things are not very welcome in heterocyclic chemistry. If you can avoid those reactions, that is much preferred. And so, in this case, and what you they have done, and they have used silver carbonate and benzoic acid, then acetonitride and 60 degree and the product is as obvious now, it is this amination, direct amination, and then you can write rest of the things. So, so you can do it direct amination without affecting the OA methoxy group, without affecting the other nitrogen, without affecting this lactone ring, you can do it. But what is the role of silver carbonate? Silver carbonate is in this case is the oxidant. So, two hydrogens are getting eliminated. So, it is an oxidant and this equivalence is required is this. Okay. So, we have seen alkylation, alkynylation and this example. Now, amination now. So, now let us look at if we can let us say substitute an alkene or alkyne or amine by an arene, and that whether this is possible or not. Like one of the simplest example which thiophene. Thiophene normally is a popular molecule in polymer chemistry, because polythiophenes are conducting polymers, and in the R here is an ester, or it could be ester, it could be acyl group, or even it could be methyl group. And if you react these with palladium chloride, acetonite, sorry, benzonitrile complex and DMSO, then 60 degree again. So, I write all these details of the reaction condition just to give you a feel about the okay. So, what do you expect? And it's a quick that means it's a dimerizations, it's a nice dimerization, that is it. So, what is the intermediate? Intermediate is, you can say, the first thing, the first intermediate could be that electrophilic substitution reactions of thiophene with palladium X, and then once you have palladium X, second molecule come, right. Second molecule this X can undergo again electrophilic substitution reactions with another molecule. So, eventually we will get a palladated bis-thiophene, right, palladated bis-thiophene and bis-thiophene. Then what? Then reductive eliminations minus palladium 0. Okay. And so, to speed up the second step, first step is quite easy, because palladium 2 is pretty electrophilic in nature, but this one is not very electrophilic in nature. So, what you have to do? You have to make this little more electrophilic. How do you do? You have to make this electrophilic. Add silver fluoride, and in this case obviously you have to use because halogen is there. So, you have to use 2 equivalents of the silver fluoride. Okay. And dichloro phenyl cyanide, yes, palladium chloride. It's a complex. It's a complex. It's a complex. And very recently something else is coming up. There is a, I think I'll just we stop here. There are so many other examples on these kinds, very similar. That means in principle that dehydrogenative reactions can be feasible, and like even if you let us say these are the reactions possible also. If you take an indole and a substituted indole, say substituted indole and plus benzene, of course palladium trifluoroacetate, you can go to this. Eventually what you will find under certain conditions you can directly do the arrylations, you do not have to do any metalloids, any standard traditional cross coupling reactions, that's okay. And I think I will give you the last example. We have so many examples, but this is a topic which is coming up quite fast. And if you take, let us say furic acid, then acrylate, and again Pa, which I call palladium acetate, oxygen and DMSO, DMSO, whatever, and just heat it, right. What would you expect? You would expect again a dehydrogenative kind of thing, because palladium is there, etc., etc. But when you have a carboxylic acid, the reaction goes, is called known as decarboxylative. Okay. So, and this is it is coming up, this reaction is coming up, and you can, so advantage is a regis specific, means it will only alkylate at the place of the carboxylic acid group. In the previous cases, you know that it sometimes they are not, the reactions are not very regis selective. So, what is the summary? Summary is that you can do away with metals and metalloids. So, I mean, if you know how to tune the reactions conditions, I mean a little bit of the reaction mechanism. Reaction mechanisms normally involves oxidative additions or the electrophilic substitution reactions or electrophilic additions of the palladium 2. So, these are the two important possibilities. If you keep them in mind, then it is easy to tune the reaction. And what else? And occasionally you can activate palladium by silver, addition of silver. Third point that you need to remember. What is the third point? Kinds of oxidizing agents which are compatible with heterocyclic compounds, because there are not many heterocyclic oxidant which would permit these sort of reactions. Okay. What how many types of oxidants we have come across today? Benzoquinone, sometimes DDQ also used. Benzoquinone is very similar to DDQ. Oxygen, of course, air, silver carbonate, cupric acetate. Cupric acetate also is a very useful one, especially in case of decarboxylative reactions. So why? You know why, right? Why? Any guess? Cupric salts are very useful in decarboxylative coupling reactions. Bolo. Because okay, let us say how do you decarboxylate benzoic acid in lab?